Good evening and welcome to another episode of Maths in an Empty Classroom with me, Mr. Southern. This lesson is on kinematics, non-constant acceleration, so it's a mechanics topic. First thing I want to do is to revisit something that you've studied in mechanics already, which is vertical motion. And I want you to consider that you project something from the ground with an initial velocity u of 39.2 metres per second. And because it's vertical motion, we consider this particle to be moving freely under gravity, and therefore the acceleration of that particle would be negative 9.8 ms to the minus 2. So negative because it's going downwards, 9.8 metres per second. Now if we think about the equation of motion, the Suvat equation that we would use for displacement, we would use S equals ut plus half at squared. And if we substituted the value of u and a into that equation, that would give us S equals 39.2t minus 4.9 t squared. If we wanted to find the velocity of the particle at a particular point, we would use the Suvat equation v equals u plus at, and substituting the numbers into that equation, we have that v equals 39.2 minus 9.8t. So u is 39.2, a is minus 9.8. And the reason I'm getting you to think about this is I want you to consider the relationship between this equation here for displacement and this equation here for velocity. And just looking at the coefficients and what's happening to the powers of t, what you should notice is, well, actually, if I differentiate this equation here for s, I get this equation for v. So you differentiate 39.2t, you get 39.2. If you differentiate 4.9t squared, timesing the 4.9 by 2, 9.8, reducing the power by 1 is 1. So if you differentiate displacement, you get velocity. And that should make sense, because what is velocity? Well, velocity is how fast you're moving. It's the rate at which your position is changing. So if you move faster, you change position more quickly. So it's all to do with rates of change. So I'm just trying to get you to understand about how calculus, rates of change, can be used with kinematics. Another way that you can think about it is your displacement, which is in meters, your velocity is in ms to the minus 1. If we were going to look at acceleration, then acceleration, the unit of that one would be ms to the minus 2. And you can see that what's happening is the power is reducing by 1. So actually, if you differentiate displacement, you get velocity. And if you differentiate velocity, you get acceleration, which again should make sense, because what is acceleration? Well, acceleration is the rate of change of velocity. And if I go back to here, if I differentiate this equation again, differentiating a number, 39.2, that's going to go to 0. Differentiate negative 9.8t, I'm going to get negative 9.8, which is the value for acceleration that I know because it's moving under gravity. So you can see, start with position, differentiate to find velocity, velocity, differentiate to find acceleration. I'm just going to do a very quick sketch of the curve of the displacement of what that would look like, just so we can visualise this problem a little bit here. So with displacement, it's starting from the ground, and it's going to be a parabola that looks like that, and this is S for displacement. So what's happening here is this is modelling the position of the particle. So we project it from the ground, it's going up, it reaches its maximum height here, and then it starts to fall back down to the ground to return to its initial position due to gravity. And what I just want you to think about is, if you were to draw a tangent at any point to this graph, this tangent would tell you the velocity. So what we can see is, if I trace my ruler as the tangent going along this line, its gradient is decreasing, so the velocity, the speed of the particle is decreasing until it gets to its greatest height here at the point where v equals 0. So that is the maximum distance away. And then what starts to happen is the particle starts to fall to the ground, so its speed is increasing, so its velocity is getting more and more negative as it accelerates towards the ground. The gradient of the tangent is getting steeper, but it's negative because the particle is falling. So everything you know about calculus that you've done so far with differentiation is now going to be applied to non-constant acceleration. So tangents, turning points, rates of change, all that language that you're already familiar with, we're just going to apply that now to situations where you have non-constant acceleration. So in the next video, I'll go through a specific example of how we would apply this.